My name is Miguel Flores, and this is my Physics 2211 Lab 1 on constant velocity. The content we'll be going over today includes our introduction, fundamental principles, procedures, data analysis and conclusions, possible errors, and further questions. Our introduction. The purpose of Lab 1 is to observe the motion of a moving object going at a constant speed without changing directions and compare the observed position to the predicted position that is computed from a computational model. Our object includes our weight. Observed position will be found using Tracker, and our predicted position will be found using Glowscript. This lab will allow us to see the principles of Newton's second law in real time. Some of the fundamental principles we'll be going over throughout this lab includes Newton's first law, which states zero net interactions, Newton's second law, which is force equal to mass times acceleration, our constant velocity, which is our net force equal to zero, and some of the basic formulas such as our velocity update formula, where we set final velocity equal to our initial velocity plus net force over mass times our change in time. Position update formula, which includes our final position set equal to our initial position plus average velocity times our change in time. Newton's second law, and average velocity formula, which is our change in position over our change in time. Our procedure. We'll record a video of a weight rolling in a straight line at a constant speed. We'll import the video into Tracker and track the weight frame by frame at set time intervals. We'll create a computational model of the predicted position of the weight in Glowscript utilizing the provided starter code. We'll generate a spreadsheet of the observed and the predicted positions and graph the data over time. And we'll graphically compare both models and draw conclusions. Alright, now talking about our systems and surroundings. Our system includes the weight, and our surroundings include the floor and gravity. So, some of our tracker analysis. Our total time was found to be 2.033 seconds. Our initial position was found to be 0.000103 meters in the x direction, and our initial velocity was found using our change in position over change in time, which we found to be 0.599 meters per second in the x direction. Now for the fun part, our code. We got to change our starter code, and we set our mass equal to the mass of the weight, which is 0.1 kilograms. We input our initial position and velocity found in the previous slides. We updated delta t to 0.33 seconds, which is the change in every frame, and our total time to 2.033 seconds, which was the time of our video. We set the net force equal to 0, and we input our velocity update and position update formulas in order for our code to compute these for each time interval. Now, we have our two different graphs. Our top graph shows our tracker graph, which is our observed data, and we have our Glowscript graph, which is our predicted data. And as we can see, our observed graph begins to kind of become more sloped and horizontal, while our Glowscript data is completely linear throughout the time period. Now, our computational model analysis. After running our code through Glowscript, it results in a 3D visual model from our weight rolling from position A to position B, and results in a position time graph for our computational model, which is completely linear. We also get a velocity time graph, which is completely horizontal slope, showcasing a constant velocity throughout the time period. Some of the different possible errors include outside or unaccounted for forces such as friction or air resistance, human error using Tracker, which is not choosing the correct center of mass, and rounding or computing errors, which can affect accurate results. Some of the further questions that one may have: what if the x and negative x axes were interchanged? If the x and negative x axes were interchanged, the slope of our graph would be completely the same, just in a negative downward slope. And what does this information mean? Or is it possible for to say how many pushes and pulls or forces are being added together to give zero net force in the case that we observe? Since our computational model using Glowscript is not accurate compared to our observed model, and we can see our observed model becoming more horizontal as time goes on, one may conclude that there are other forces acting upon our system which set the net force to be different from zero. However, it would be impossible to tell how many or which forces they may be due to the complexities of our physics course. Thank you so much for your time. Have a great day.